We are starting the second video, utility. And utility is going to be more into like, we're going to actually start doing some things with this, right? And so our utility is the goods that provide well-being, and we represent that with a utility function. And so the utility function is the relationship between every possible bundle of goods. So we're going to have every possible combination of X and every possible combination of Y, and those are going to lead to different combinations of U, right? And so we're going to have a ton of utility functions, right? They could be multiplicative, they could be additive, they could be in the square root function, they could be whatever, right? But there's going to be a couple other things that we need to deal with this, and we're going to first call these marginal utilities, right? And so we talked a little bit about diminishing marginal utility, but if we wanted to do this mathematically, marginal utility is simply just the derivative, the partial derivative of u with respect to whatever variable of interest. And so this would be the marginal utility of x. So the marginal utility of x, right? And very similarly, if we wanted du dy, we would get the marginal utility of y, right? And so that's the only thing that we really need to like really kind of understand about utility is that everything is not made in totality. Like, yes, we do prefer 100 to not like to 50, right? That is true, right? That is not what I necessarily mean by totality. But on the margins, if we're choosing to benefit, like if we're choosing to spend our extra unit of goods, right? If we've got this extra money, ultimately we're going to be making those decisions every time, right? We're not going to just say, okay, yeah, we're going to buy 100 units because we've got the money to pay for that. If our marginal benefit of buying that additional donut, buying that additional beer is not worth the cost to do so, then we're not going to do it, right? We're going to keep our money, we're going to go home, typically. Or we're going to buy it on the other good, which is what we're going to see in this class, right? Is that we're going to always spend all of our money, so we're not just going to go home. But if the marginal utility of one is bigger than the marginal utility of the other, then we're going to buy the marginal utility where the marginal utility is bigger, right? And so utility functions are also use ordinal rankings. So we use A is preferred to B, not necessarily cardinal rankings, but that doesn't really matter. Now we've got this idea called this marginal rate of substitution. And so the marginal rate of substitution is the maximum amount of one good that a consumer can sacrifice um, to obtain one more unit of another good and be on the same level of utility, right? So stay on the same indifference curve. And so what we have here is that we've got this slope of the indifference curve is just the change in the quantity of one good over the other. So if we wanted the slope of the IC, then this is just going to be the change in good one over the change in good two quantity, which is equal to obviously the change in, let's just call this x over the change in y, which is just our derivative of x with respect to y, or our marginal rate of substitution between x and y. Right, and that looks exactly like what a derivative is, right? When we're thinking about the slope of a line, we're thinking about the change in rise. But again, this doesn't really matter because we can flip them. If we put x and 1, so here maybe we should do this instead so that we can think about mm, okay, got it. I don't know what that's going to do to me, but we could do something like that where we'll have the change in y rise over run, but it doesn't matter. It doesn't matter. I actually think that's going to screw me up. I don't know how to fix that on the fly though. So, oh well. But notice that our marginal rate of substitution is always going to be negative. If we're going to increase in y, we're going to have to decrease in x and vice versa. If we increase in x, we're going to have to decrease in y. And so one of them is always going to be negative. And so our marginal rate of substitution will always be negative. This is due to our trade-offs. And the changing of the IC slope is consistent with your preferences due to diminishing marginal returns. Um, and yeah, so we just have the slope changes over the IC, over the indifference curve, right? If we have something that looks like this, we've got good X and good Y, and our indifference curve looks like this, then obviously our slope is going to change throughout because it's nonlinear and will be solid. So let's compare marginal rate of substitution and marginal utility now, right? These are the two things we've thrown around the word margin a lot. Um, it's just kind of what are we going to deal with these between, right? And so the marginal utility of good one is, again, the derivative of utility with respect to good one. It's going to be the extra utility that you would get from consuming that last unit of good, holding the other ones. So if we think back to our beers and donuts example, it's going to be the extra unit of benefit that you would get from eating another donut, holding the number of beers you've drank constant, or vice versa, getting the extra sip of beer, holding the number of donuts that you've eaten constant. And so oftentimes you will see these derivatives written with a subscript 1 underneath. This just means that we're going to take the derivative with respect to the first good or good 1. It would be the same thing as writing Q1, and it would also be the same thing as saying something like this. Right, so those are all the same, but sometimes it's a lot easier just to write this than it is to write the whole thing out. And so we're going to say the derivative of this utility function with respect to this first good should be 1/2 times the inside times the derivative of the inside. And it's going to be symmetrical for you too. Out here, right? And so remember that our MRS is equal to dq2 over dq1. So it is just how much does Q2 have to change if we increase Q1 by 1 unit such that we're keeping the utility constant? Okay, that's the big thing when we're dealing with marginal rate of substitution. So now, if we wanted to think about this a little bit further, right, let's let this implicit function exist, right? And we remember what implicit functions are, right, from the last chapter. Essentially, what this means is that if we come back up here, we want this utility to be constant, right? Want to be constant for the marginal rate of substitution, right? So to kind of link these back and forth, right? So how much of Q1, Q2 has to change to keep U constant if Q1 increases by 1 unit. Okay, so if we let this function Q1 and Q2 be like Q2 be a function of Q or Q1 be a function of Q2, be an implicit function, then we can write our U as a function of only Q2, right? And so let's differentiate. So let's diff with respect to Q2. And so we're going to get du star dq2, or again, we could do something like this. And we're going to get this partial derivative of u of q1 of q2 over with respect to Q1 times dQ1 dQ2 plus this marginal change in U following a change in Q2. I think we're okay with that. Sorry, this is sloppy math, guys. And so, if we solve, we get minus the utility of 1 over the utility of 2, right? Which is exactly what we were thinking over here, right? So let's do an example. So let's find this marginal rate of substitution for this Cobb-Douglas utility function, which is just a fancy way of saying that our exponents sum to 1, right? A times 1 plus, A plus 1 minus A is going to just be 1, right? And so if we wanted to think about this in kind of like a cheating way, we could do this in a couple different ways. The first one is we're just going to kind of like throw out a formula, right? We're just going to treat it, we're going to do everything, and then we are going to, the second one, we're going to do an example with it. And so we should be okay. And so first, let's take our marginal utility of 1. All right, and so this is going to be du dq1, right, which should be a q1, a minus 1, q2, 1 minus a. The marginal utility of 2 should be very similar times minus a, because the ones are going to cancel out. And so then our marginal rate of substitution is going to be minus the marginal utility of a, or of 1, over the marginal utility of 2. And so, and notice that like sometimes we flip-flopped, sometimes it was 2 over 1, sometimes it was 1 over 2. Since we're giving up, it just depends on how you want to interpret it. Since we're giving up goods both ways, the rate of substitution will go both ways. It'll just be like, let's say we get 2 beers for every donut, or 2 donuts for every beer. That would just mean that for every donut, we get half a beer or something like that, right? It just depends on how you want to interpret it, but it doesn't matter really what direction you go in. And so we are going to get something that looks like this. And if we do some fancy simplifications, we get a over 1 minus a. And then we're going to get a minus 1 over a. And so this is going to flip, right? So we've got q1 A minus 1 minus A. This is going to flip Q1 downstairs. Same thing with Q2. And so this would be the formula for your marginal rate of substitution of a Cobb-Douglas utility function. Okay? So if we wanted to do an example with this, right, let's figure out what the marginal rate of substitution is. If we're given utility equals Q1 0.4, Q2 0.6, and here, actually, let's write this a little bit better. Let's give ourselves a box to be cleaner. So if we wanted now, and then let's say that Q1 equals 24 and Q2 should equal 18. Then, using our fancy marginal rate of substitution formula, we should get 0.4 over 0.6 times 18 over 24, which should be something like minus 1/2. And that's it. That's the marginal rate of substitution. So it means that for every good, every time that we're going to get an increase in good 2, we need to decrease our consumption of good 1 by a half. So, or by half a unit, so that we can keep our utility constant. Okay? And so there's some other indifference curves that we're going to be dealing with, right? We're going to talk a lot about perfect substitutes. And perfect substitutes are pretty easy. They're pretty straightforward. Um, they have a pretty goofy looking indifference curve map. There's, because you are completely indifferent between the two goods, rather than it being downward sloping, it has a constant marginal rate of substitution. And so your indifference curves just look like this. Rather than being downward sloping. And so again, if this was good X and Y, it doesn't matter. When the consumer prefers the two goods equally, that you just have straight line indifference curves. And so you should be okay with that. And again, remember, this marginal rate of substitution is going to be the slope of the indifference curve at a given point. And so for this, at any given point, it's going to have a constant marginal rate of substitution. And so we'll be perfect with that. Right? The second thing is we're going to have this thing called perfect complements. And perfect complements means that we always consume things in fixed proportions. So my favorite example of perfect complements is shoes. You're not going to buy 100 left shoes if you don't have a right shoe, right? You always are going to buy shoes in pairs, right? It doesn't matter how many left feet you have if you only have one right-footed shoe. And so their indifference curves look like right angles. Because regardless of how many left-footed shoes you have, if we were thinking left, like if we were thinking this is left shoes, if you only have the one right-footed shoe, it doesn't matter. Like you're going to get the same utility regardless. And so that's where this minimum operator comes in. And the minimum operator is pretty easy. It looks scary because it's like, oh my God, I don't know how to differentiate that. It just essentially says that comparing both of those numbers, take whatever's the smallest one, and that's going to be your utility, right? So if we had 100 shoes over here, like let's say this was 100, but we only had one right shoe, then our utility is just going to be whatever our utility of one pair of shoes would be. Okay? And so now we're going to get into this thing called the budget constraint. And the budget constraint is pretty straightforward. We're going to have income or our budget, and we are going to be consuming this in fixed proportions, right? And so we're only going to do this in one day, right? And so you're not going to save, we're not going to do anything. We're always just going to spend our entire income on these two goods. And so let's assume that we can do that, right? So our Y is our income or our budget. The P1, Q1 is the thing that we're going to be spending on good one, right? So it's our quantity times our price per quantity for good one, and the same thing for good two. And so the first thing is we're going to solve for Q1, I mean Q2 in terms of Q1, right? So if we take Y minus P1 Q1 should equal P2 Q2, then Q2 should equal Y minus P1 Q1 over P2. Okay? Or if we wanted to split this up to make graphing a little bit easier, we could do something like that, right? And so if we wanted to plot this on a graph, right, we're going to take Q1 again and Q2 over here. And now we've got a function Q2 as an input that takes inputs from Q1. And so on our x-axis, this is going to be when Q2 is equal to 0. And so if Q2 is equal to 0, y over P2, P1 over P2, Q1, or in another way, like a very more, let's do this in a bit more direct way instead of using this. If Q2 is equal to 0, that means that this term goes to 0. And so our P1, our Q1 should be y over P1. We're going to do y over P1. And very similarly for Q2, this would be y over P2. And then you just plot the two intercepts, draw your budget line, and our slope is going to be the negative ratio of the prices. That's the budget constraint. That's it. We've got our vertical intercept, we've got our horizontal intercept, we've got everything that we're going to need. Now we can start to combine indifference curves and budget constraints to make things super cool. But yeah, that'll be in the next video. Thanks so much, and we'll see you in video 3.